Have you ever stopped to really think about the invisible world inside your smartphone? Or maybe your smart speaker, or even those, huge AI servers humming away somewhere.
Yeah, it's kind of mind-boggling.
Right, we're talking about the tiny chips that power literally everything. It's not magic, but it feels close sometimes, doesn't it?
It's just brilliant engineering, really.
Absolutely, and it relies on these incredibly precise languages to make sure those complex digital brains work exactly as intended every single time.
And today, we're going to pull back the curtain a bit on one of the real unsung heroes of this whole intricate world, System Verilog. It's this critical language for designing, yes, but maybe even more profoundly, for verifying these incredibly complex digital systems.
The verification part is huge.
So our mission today in this deep dive is to really distill insights from, well, a stack of sources, the actual IE standard itself, insights from industry experts. We want to help you understand what System Verilog is, why it's become so indispensable, and how it helps engineers build reliable chips faster. Think of it like a shortcut, maybe, to understanding the backbone of modern hardware development.
Exactly. I know hardware description language might sound a bit dry, maybe. But trust us, we're going to make it accessible and hopefully reveal some genuinely surprising insights that might just change how you think about the tech in your pocket.
Sounds good.
Okay, let's dive right in. At its core, what is System Verilog?
Okay, so at its heart, System Verilog is formally known as IE 1800. It's what we call a comprehensive hardware description and hardware verification language. An HDVL.
HDVDL.
Right. Its main purpose is, well, everything from modeling and designing electronic systems to simulating them, testing them, and ultimately implementing them in silicon.
And it works at different levels.
Exactly. That's one of its strengths. It supports describing hardware at various levels of abstraction.
Yeah.
From high-level behavioral models, just capturing the function, down to RTL, register transfer level, which is more about data flow and storage.
Closer to the hardware.
Right. And even down to gate-level representations, which are very close to the physical layout.
What I find really fascinating is how it all came together. You mentioned it's a unified language. What was that journey like? What problems were engineers actually facing before this unification happened?
That's a great question because the unification really is the game changer here. System Verilog's roots go back to 2002 with a language called Superlog that was aimed at enhancing hardware description.
Okay.
And around the same time, Synopsys developed OpenVera, which was specifically built to tackle the growing verification challenges. The chips were just getting too complex to test easily.
Right.
But the really pivotal moment came in 2009. That's when the existing Verilog standard, IEE 1364-2005, was formally merged into the System Verilog standard. That became IE 1800-2009.
So before that merger, it sounds like things were a bit fragmented.
Fragmented's a good word.
Yeah.
Designers might be using one version of Verilog for their hardware design, but then the verification team might be using a completely separate language or maybe complex custom scripts.
That sounds like a recipe for problems.
Oh, it was. We used to talk about tool chain headaches. You had different tools, complex APIs trying to connect these different language environments. And critically, you had misinterpretations between the design teams and the verification teams.
Like they weren't speaking the same language, literally.
Pretty much. The designers would hand off a chip design, and the verification folks might struggle to properly test it because their tools and methods weren't, fluently connected to the design description.
So this merger in 2009 created this single cohesive language for both design and verification. That must have just fundamentally changed the workflow.
Absolutely. It created a common linguistic ground, which is just crucial for preventing misinterpretations. Designers can now better understand the verification test benches, and the verification engineers can more accurately get the design intent.
Makes sense.
And if you think about the bigger picture, managing complexity in chip development, we're talking billions of transistors now. Having that cohesive approach is vital. It reduces errors, boosts productivity, and ultimately helps get reliable chips to market faster.
Okay, that makes perfect sense. So, given that history, how did we actually get to System Verilog's dominance, especially when you consider other languages out there? And maybe we can trace Verilog's own journey a bit further.
Sure. Verilog itself started way back early 1980s as a proprietary language. Then it went public under Open Verilog International, or OVI. That led to its first standardization, IEE 1364-1995, Verilog 95.
Right.
Later versions like Verilog 2001 and 2005 added important features like sign types, generate loops, file I/O, things like that. But then we hit this critical bottleneck.
The bottleneck being complexity.
Exactly. As system on chips, basically an entire computer system on one chip got incredibly complex, the traditional testing methods just weren't cutting it anymore. Well, imagine trying to manually write tests for every single possible interaction on a chip with billions of transistors. It's impossible. Earlier Verilog versions only had pretty basic testing constructs. They were just inadequate for finding the tricky bugs in these really intricate designs.
So System Verilog had to step up.
Precisely. It emerged as a necessary extension. It pulled in advanced verification features, borrowing heavily from things like OpenVera. That's where capabilities like object-oriented programming, constrained random generation, assertions, functional coverage, all that powerful stuff came in.
And Verilog itself.
Verilog, as we knew it, is now officially just a subset of System Verilog. System Verilog is the superset.
Okay. Now, when people talk about hardware description languages, another big name always comes up, VHDL, often seen as, the other main player. How do they stack up against System Verilog, and why has System Verilog become so dominant in many areas?
Right, VHDL. That's the very high-speed integrated circuit hardware description language. Is definitely prominent. It's known for being very strongly typed and having a more verbose Ada-like syntax.
Ada-like, okay. Different feel from Verilog's C-like style.
Very different. And because of that strong typing, VHDL is often preferred for designs where reliability and safety are absolutely paramount. Think aerospace, maybe automotive applications, places where preventing errors up front is the highest priority.
And Verilog?
Verilog historically had that simpler, C-like syntax, looser typing. It was generally seen as quicker for describing standard digital logic. System Verilog then builds on that Verilog foundation.
But it adds the power-ups.
Exactly. It adds the crucial object-oriented programming and those advanced verification features that we mentioned. That's the key differentiator.
Can we get a bit more specific on those differences, like typing?
Sure. VHDL, strongly typed, great for catching type errors early. Original Verilog, loosely typed, more flexible, but potentially more error-prone. System Verilog, it finds a kind of middle ground. It offers much richer data types than Verilog and stronger type checking, but maybe not quite as strict as VHDL. Static but weakly typed is the technical term.
And their primary focus?
VHDL's focus was really design rigor. Verilog is more about basic circuit description, speed of writing. System Verilog stands out because it's designed from the ground up as a unified HDVL for design and specification and robust verification.
And OOP support, verification features.
Big difference there. Extensive OOP support in System Verilog, limited or none in the others. And those advanced verification features constrained random verification, CRV, assertions, functional coverage, the whole UVM framework that's really System Verilog's domain.
Right.
The others have very limited capabilities there.
So if VHDL is known for its rigor, why did System Verilog seem to surge ahead in the broader semiconductor industry, especially for complex chips?
Well, I think the industry choice reflects a very pragmatic balance, right? You've got speed, reliability, rigor. VHDL prioritizes error prevention through its strictness. Classic Verilog leaned towards ease of use, getting designs down quickly.
And System Verilog?
System Verilog hit this sweet spot. It combined Verilog's relative design simplicity with these powerful, almost software-like features for verification. And that verification capability became absolutely critical for complex sauce development.
Because the testing problem just exploded.
Exactly. The sheer volume of tests needed meant you just couldn't rely on manual directed tests anymore.
Yeah.
You needed automation, constrained random coverage metrics, all the stuff System Verilog brought to the table. The ability to create reusable, scalable verification environments was the killer app, really.
That makes a lot of sense. It really sounds like System Verilog filled this gap that just kept getting wider as chips got more complex. Is it still in either situation today, or is it more nuanced?
Oh, it's definitely more nuanced. You see mixed language flows quite often in the industry.
Like using both?
Yeah. For instance, a team might use VHDL for the core RTL design of a really critical safety-focused part, leveraging its strong typing. But then they might use System Verilog for the test bench to verify that VHDL block. So, while System Verilog is clearly the dominant force in modern verification, especially for large SOCs, understanding the whole HDL landscape is still valuable. Engineers often pick the best tool for the specific job at hand. It's a dynamic field.
Okay, we've covered the roots, the unification, the comparison with VHDL. Now let's peel back another layer. What specific tools does System Verilog give hardware designers for actually building the hardware? beyond just the verification side.
Right. System Verilog significantly beefs up Verilog's design capabilities, too. It gives designers much more powerful and, crucially, more explicit building blocks for managing complexity.
Explicit seems like a key word there.
It is. Take the logic type, for instance. Before logic, you had reg and wire types in Verilog, and the distinction could sometimes lead to subtle bugs, especially around multiple drivers.
Ah, yeah. Multiple things trying to control the same signal. Bad news.
Exactly. Logic simplifies this. It's a four-state type like reg. But the key is that synthesis tools generally enforce a single driver rule for it in most contexts. It makes your design intent clearer. This signal should only be driven from one place. It helps prevent those kinds of errors.
So it's about reducing ambiguity. I remember struggling with unintended latches early on, like chasing ghosts. These specialized blocks sound helpful there.
They are huge for that. Verilog just have the general always block. You had to be careful with your sensitivity list, or you could accidentally infer latches or miss updates.
Right, forgetting a signal in the list.
Yep, classic bug. System Verilog introduces specialized blocks that make your intent crystal clear. Always come as specifically for combinational logic. The beauty is it automatically infers the sensitivity list from the logic inside the block.
Oh, that's nice.
Yeah, it prevents that whole class of bugs. Plus, it tells synthesis tools, no latches intended here. Then you have always latch specifically for level-sensitive latches.
Yeah.
Again, with inferred sensitivity.
And for flip-flops?
That's always Gareth. It's for synchronous edge-triggered logic. It enforces that assignments happen only on clock edges. These specialized blocks really reduce bugs by enforcing stricter rules and making your design intent totally explicit to both humans and the EDA tools.
So better code, fewer bugs. Makes sense. What about handling data?
System Verilog gives you much richer data types. We mentioned logic. You also get multi-dimensional packed arrays. These kind of unify the old Verilog concepts of registers and memories and lets you manipulate blocks of bits really efficiently. Crucial for things like data paths.
And enums. Enumerated types. I know those from software.
Exactly. They bring that same benefit to hardware. Instead of using raw numbers like parameter idly equals 2 to 0, 0, 0, 0, 0, 0, 0, you can just define an enum, idle, fetch, decode.
Much more readable.
Way more readable and maintainable. Plus, it adds type safety. The tools can check that you're only assigning valid states. There's even a handy .name function to get the string name, which is great for debugging or messages.
You also mentioned new integer types.
Right. Things like byte, shortened, ints, longint. These are two-state types, meaning they only hold 0 or 1, unlike the four-state types, logic, reg, which also have X for unknown and Z for high impedance.
Why is that useful?
Two-state types can often lead to faster simulations because the simulator doesn't have to track those extra X and Z states. They behave more like software integers. You also get bit, which is a variable with two-state type.
And structures and unions, like in C.
Yep, very similar. You can group related data together. The really important thing for hardware is the packed keyword. A packed struct guarantees that its elements are stored in a contiguous block of memory, bit for bit.
Which matters for synthesis, right? How things map to hardware.
Absolutely. How data is laid out is critical in hardware. Packed gives you that control. You can also have unpacked structs and unions, which behave more like C. And type defs let you create custom names for complex types, again, improving readability.
What about data lifetime? Static versus automatic.
Yeah, that gives you control over when variables exist. Static variables, the default in modules, exist for the entire simulation. Automatic variables, typically used in tasks or functions, are created when you enter that scope and destroyed when you leave. More like local variables in software. It allows for things like recursion and reentrant tasks.
Okay, so more refined building blocks, better data handling. What about putting these blocks together? Reusability sounds key.
Definitely. Modules are still the fundamental building blocks, like in Verilog. But System Verilog significantly enhances parameterization.
How so?
You can declare parameters within a module definition, maybe for the data width of an ALU or the depth of a memory. Then, when you instantiate that module, you can provide specific values for those parameters.
So you can reuse the same ALU code for a 32-bit version and a 64-bit version.
Exactly. You just change the parameter value during instantiation. It massively improves reusability and reduces code duplication. You can specify types for parameters now, too, like parameter int. WIDTH is 32.
And local param? What's that?
Local param is like a constant within the module. Its value is fixed within the module definition and can't be changed when you instantiate it. It's great for internal constants, derived values based on parameters, things like that. Helps keep things clean.
Good practice to use those for internal calculations then.
Yeah, definitely. keeps things tidy and prevents accidental modification.
Now, when designs get really big, thousands of ports connecting modules, managing that connectivity must be a nightmare. How do interfaces help?
Interfaces are a lifesaver for large designs. They let you bundle a whole group of related signals, like all the signals for an AXI bus, for instance, into a single object, an interface.
So instead of connecting hundreds of wires individually,
You just connect the single interface instance between your modules.
yeah.
It drastically reduces the amount of code, cuts down on connection errors, and makes the top-level design much, much cleaner and easier to understand.
That sounds incredibly useful. What about signal directions?
That's where mod ports come in. Inside an interface, you can define module ports, which specify the direction of each signal, input, output, in-out, for a specific perspective.
Like a master versus a slave view of a bus.
Exactly. The master module would connect using the master mod port, and the slave using the slave mod port. The compiler checks that the connections match the directions defined in the mod port. It adds another layer of checking and clarity.
Are interfaces actually synthesized into hardware?
Generally, no. Interfaces themselves are typically not synthesizable, especially the more complex features. Their main power lies in abstraction and simplifying connections, particularly between the design, DUT, and the verification test bench. They are fantastic for building reusable and configurable test environments.
Okay, so abstraction is key there for both design clarity and verification setup.
It really helps manage that complexity explosion we keep talking about.
Right. So these design features clearly streamline building the hardware, but we keep coming back to verification being System Verilog's true superpower.
Yeah.
Why is that aspect so critical?
Well, like we said, modern chips are just staggeringly complex. Billions of transistors, intricate interactions, traditional directed testing where you manually write tests for specific scenarios simply cannot find all the potential bugs. It doesn't scale.
You just can't think of every possibility.
Exactly. And the cost of finding a bug after the chip is made, it's enormous.
Oh.
So you absolutely need more sophisticated verification methodologies. System Verilog provides the language foundation for these.
Which brings us to constrained random verification, CRV. What's the core idea there?
The core idea of CRV is to automate the generation of test stimuli, but in a smart way. Instead of writing specific test cases one by one, you define the kinds of inputs you want, specify constraints on those inputs, and then let the tool randomly generate thousands or millions of valid test scenarios within those constraints.
So it's random, but not completely random. It's guided.
Precisely. It's constrained random. You use randomization features like ran variables in classes, which get assigned random values when you call object.randomize.
Yeah.
There's also rangor for cyclic random variables. They cycle through all possible values before repeating.
And the constraints, how do they work?
You use the constraint keyword block within a class to define rules or relationships between the random variables. For example, you could constrain a transaction address to always be within a valid memory range, or ensure that the packet size is always non-zero. You use the with keyword with randomize sometimes, too, for inline constraints.
So you guide the randomness towards interesting or legal scenarios.
Exactly. You prove the vast space of possibilities down to the relevant ones. You can also control the distribution of random values using the dist operator. You can give certain value ranges higher weights or ensure equal probability.
Why would you want to control the distribution?
Maybe you want to hit corner cases more often or focus testing on specific modes of operation. It gives you finer control over the random stimulus to target areas you suspect might have bugs. CRV fundamentally increases the chances of hitting unexpected bugs that directed tests would likely miss.
It's like cleverly tricking the system into revealing its hidden flaws by exploring scenarios humans might not even think of.
That's a good way to put it.
Okay, beyond CRV, there's assertion-based verification, ABV. How does that fit in?
ABV is about formally specifying expected behavior directly within the code or alongside it. Assertions act like monitors that constantly check if the design is behaving according to its specification during simulation.
So instead of checking outputs at the end of a test, you're checking rules continuously.
Right. It helps catch bugs much closer to the source, drastically reducing debug time. It's about defining what must always be true, or what should never happen.
What kinds of assertions are there?
There are two main types. Immediate assertions use the assert keyword directly in procedural code. They check a condition right when that line is executed. They're useful for specific checks, like ensuring a reset condition is met. But you have to be careful about race conditions with them.
Okay. And the other type?
The more powerful type for most design properties is concurrent assertions. These use property and assert property. They define behavior over time and synchronize to a clock. They're ideal for checking things like bus protocols, state machine transitions, timing relationships.
How do you define behavior over time?
You build sequences and properties. Sequences describe patterns of events using temporal operators like #tag for clock cycle delays. So #tag 1B means A happens, then one clock cycle later, B happens.
Okay.
Properties then use these sequences, often with implication operators like lake overlapping or non-overlapping. For example, rec #tag 1.5 glanta means if rec is true, then gent must become true between 1 and 5 clock cycles later.
Wow, that's quite expressive.
Very. You also have repetition operators, ways to combine sequences and built-in system functions like row sig to detect a rising edge, fill sig for falling edge, stable sig to check if a signal hasn't changed, pass sig to get a previous value, and many others.
Sounds powerful. You mentioned bind files earlier in relation to assertions. Why are they important?
Ah, yes. Bind. It's a crucial practice. It lets you instantiate your assertion module or interface containing your assertions and connect it to the signals within your design module, but without actually modifying the design module source code.
So the assertion code lives separately.
Exactly. It keeps your RTL design code pristine, clean, uncluttered, and free of verification-specific code that might confuse synthesis tools. It also makes managing and debugging assertions much easier. You can swap assertion sets in or out using different bind files.
Got it. Keep design and verification separate where possible. Now, what about functional coverage? How does that complement CRV and ABV?
Functional coverage answers the question. How much of the intended functionality, as described in the test plan, have we actually exercised? CRV generates lots of tests, ABV checks behavior, but coverage tells you what specific features and scenarios have been hit.
So it measures the thoroughness of your random testing.
Precisely. It's a user-defined metric. You create a cover group, typically within a class or interface. Inside the cover group, you define coverage points, cover point, that monitor specific variables or expressions in your design or test bench.
And how do you measure coverage on a point?
You define bins. Bins specify the values or transitions you care about for that cover point. For example, for a state machine variable, you might define a bin for each state, IDLE, FTG, etc. The simulator tracks how many times each bin is hit during the simulation run. You can also use if to conditionally disable coverage for a point under certain conditions.
What about interactions between different things?
That's where cross-coverage comes in. It's crucial. You use the cross keyword to define coverage measurement across multiple cover points. For example, you might want to ensure you've tested all combinations of packet types and packet lengths.
Ah, so making sure feature A works correctly under all conditions of feature B.
Exactly. Cross-coverage helps find those tricky interaction bugs. You can use operators like binsoft to select specific bins for the cross.
So CRV generates tests, ABV checks rules, and functional coverage measures what got tested. It sounds like a closed loop.
It is. You run constrained random tests, check assertions, and measure coverage. If the coverage goals aren't met, you might adjust your constraints to generate different random stimuli, or maybe write some directed tests to hit specific uncovered scenarios. It provides a systematic way to gauge verification progress and completeness, helps you find the simulation holes.
Okay, and tying all this together is often the Universal Verification Methodology, or UVM. This sounds like the framework that orchestrates everything.
That's a perfect way to describe it. UVM is a standardized methodology framework built on top of System Verilog's object-oriented features. It provides a structured approach for building powerful, reusable, and scalable verification environments.
It sounds like it provides standard building blocks.
Exactly. It gives you a library of base classes. You have UVM object as the base for data objects like transactions, sequencedum, traveling through the test bench. And you have UVM component as the base for the structural parts of your test bench hierarchy.
Like what kind of components?
Things like drivers that take transactions and wiggle the actual pins of the DUT. Monitors that watch the DUT pins and reconstruct transactions, sequencers that manage the flow of transactions to the driver. Agents usually bundle a driver, monitor, and sequencer for a specific interface. Environments contain and coordinate agents, and scoreboards check the results. The test component sits at the top and configures everything.
Wow, okay. That's quite a structure. How does it promote reusability?
Massively. Because it's standardized, components written using UVM, like an agent for an AGX bus, can potentially be reused across different projects, or even bought from third-party vendors, verification IP or VIP. The hierarchical structure means you can build a test bench for a small block, then easily integrate that block's verification environment into a larger psycho test bench.
How does it manage coordination, like making sure things happen in the right order?
That's the UVM phasing mechanism. It defines a series of standard phases, like build phase where components are created, connect phase where they're hooked together, run phase where the actual test stimulus happens, report phase for results. All components execute these phases in sync, ensuring orderly setup, execution, and cleanup.
And configuring this complex structure.
UVM provides the UVM config. It's a centralized database for passing configuration information down the hierarchy. Tests can set configurations in the database, and components can retrieve them during the build phase. This makes test benches very flexible and configurable without changing the component code itself.
What about the UVM factory? I hear that mentioned a lot.
The factory is key for flexibility and reuse. Components and transactions are typically created using the factory's create method, not directly using new. This allows you to use factory overrides.
Overrides.
Yeah. You can tell the factory, hey, whenever someone asks to create an object of type A, give them an object of type B instead. Type B would typically be a derived class of type A, maybe with extended functionality or bug fixes. This lets you modify test bench behavior like swapping in a different driver without changing the test bench structure itself. It's a powerful polymorphism mechanism.
And handling complex protocols, like layered ones.
UVM provides patterns for that, too. You might have layering sequencers where one sequence generates high-level transactions that are translated into lower-level ones by another sequence. Or layering agents, where one agent's monitor feeds transactions to another agent's sequencer. The goal is always maximizing reuse of protocol-specific verification components. UVM really provides a kind of design pattern for verification, making these incredibly complex tasks manageable, scalable, and much more efficient.
It's really clear from all this that System Verilog isn't just a language. It's become a dominant force in the semiconductor world.
No question. Its adoption for complex SOUF design, and especially verification, is widespread. It's had a massive impact on the whole chip development process and the EDA industry.
We're talking about managing chips with billions of transistors now, right? The cost of failure is astronomical.
Absolutely. And that's why robust verification is non-negotiable. You mentioned that Wilson Research Group study from 2024. It's really telling.
Yeah, the one showing increasing adoption of System Verilog, UVM, formal methods, but also declining first silicon success rates, lowest in 2 decades, apparently.
Right. It highlights just how challenging complexity is, even with better tools. The pressure to get verification right the first time is immense. That failure rate underscores the critical need for these advanced methodologies.
What is the typical cost of a failed silicon these days? Just ballpark.
Oh, it could be catastrophic. Easily millions, sometimes hundreds of millions of dollars. You've got the cost of the mask set, the wafer fabrication, the engineering time for redesign and re-verification, plus the huge cost of lost market opportunity if your competitor gets there first.
Yikes. Okay, so getting it right is paramount. Even in the FPGA world, where VHDL was traditionally strong, System Verilog is making inroads.
Yeah, definitely seeing more interest there, especially for test benches and using System Verilog assertions, SVA. The verification benefits are compelling, regardless of the final target technology.
So to navigate this effectively, engineers really need to stick to solid coding guidelines and design patterns. What are some key ones?
Well, on the general coding style front, consistency is king. Consistent indentations, reasonable line lengths, always using begin and end for blocks and if or always statements sounds basic, but it prevents subtle bugs and makes code readable.
And for code, that's actually going to become hardware synthesizable design.
Definitely use the specialized always blocks. Always comb, always boof. They document intent and let tools help you. Prefer using the logic type over the older wire and reg for consistency. Leverage the richer data types like enums, typedefs, and structs, especially packed structs, for better organization and readability. Use local param for internal module constants.
Any cautions for synthesis?
Be a bit careful with interfaces directly in synthesizable code. While great for test benches, synthesis tool support for interfaces, especially complex ones, can sometimes be inconsistent or limited compared to standard ports. Also, avoid things like generating clocks or complex clock muxing inside. Always blocks keep clocking structures clean. Be mindful of initial values and declarations, as their synthesis behavior can differ between FPGAs and ASICs.
What about patterns for the verification side, particularly UVM?
Standard OOP design patterns become really important there. Things like using parameterized classes to create generic components, like a generic scoreboard. The singleton pattern for objects where you only ever want one instance, like a central configuration object. And definitely the factory pattern, which UVM uses heavily for that flexible polymorphic object creation we talked about. These patterns make your verification environments much more extensible and maintainable.
Even with all these powerful features and guidelines, engineers can still fall into traps, right? What are some common pitfalls?
Oh, absolutely. A big one is just misinterpreting the language semantics. Writing an assertion that looks right but doesn't actually check what you intended due to some subtlety in how sequences or properties work, or misunderstanding how constraint solver probabilities might affect your random stimulus distribution. It leads to wrong functionality being tested or missed.
Subtle errors that are hard to spot.
Very. Another pitfall is ineffective assertions or coverage. Writing assertions that are vacuously true, they always pass because the precondition never happens. Or defining coverage bins that are too broad or miss critical corner cases, giving you a false sense of security. You might have 100% coverage on paper, but still have critical verification holes.
But looks good on paper, Trap.
Exactly. And then there are performance hazards. You can write system Verilog code that is functionally correct but just runs incredibly slowly in simulation or formal verification tools, maybe creating way too many assertions on individual bits instead of wider buses, or using huge time windows in temporal assertions. It can kill your verification throughput.
It sounds like a supercar that's stuck in first gear.
Kind of, yeah. And maybe the biggest overall pitfall, especially as design scale, is relying too much on ad hoc methods or trial and error. Verification has to be planned, systematic, and scale with the design complexity. It can't be an afterthought tacked on at the end.
So how do teams avoid these pitfalls?
Well, adopting a modular approach helps verify smaller blocks thoroughly before integrating them. Leveraging commercial verification IP, VIP, for standard interfaces saves a huge amount of effort and brings in expertise. Systematic test planning is crucial. Clearly define what needs to be verified up front.
And using the tools effectively.
Right. Effective constrained randomization, really thinking about your constraints and distributions to target critical scenarios. Thorough functional coverage analysis to systematically measure what's tested and, more importantly, what isn't. And of course, adhering to robust coding guidelines and using static linting tools helps prevent many basic errors. These pitfalls are really lessons learned the hard way from countless projects. Even the most powerful tools need careful handling and a methodical approach.
Okay, well, if this deep dive has sparked your curiosity, maybe you're thinking, how can I learn more about this? The good news is there are loads of great resources out there.
There really are.
For structured learning, you can find excellent online tutorials and courses. Places like Duolos, Udemy, Coursera often have paths from beginner to advanced system Verilog.
And for definitive guides, well, the IE 1800 standard document itself is the ultimate source, though it's pretty dense reading.
Yeah, maybe not beach reading.
Probably not. But highly recommended practical books include Chris Spears' System Verilog for Verification, that's a classic, and Stuart Sutherland's System Verilog for Design. Both are excellent.
What about community help if you get stuck?
There are active online forums. The Accelera UVM System Verilog Discussions Group is one. The Designer's Guide Community Forum is another popular one for asking questions and sharing solutions.
And for more intensive professional training.
Companies like Sunburst Design, Duolos, Cadence, Synopsys, Mentor, now Siemens EDA, they all offer in-depth, often hands-on training courses.
Any practical advice for someone starting out?
A common recommendation is to get a solid grasp of basic Verilog first, understand digital design concepts, then transition to System Verilog, focusing first on the design enhancements, then diving into the verification features like assertions, coverage, and maybe eventually UVM.
And practice, practice, practice.
Absolutely. Start with small projects. Design and verify simple combinational blocks, sequential logic like counters or shift registers, maybe a small FIFO or an ALU. Build up complexity gradually. It really is a deep field, but incredibly rewarding if you're fascinated by how modern technology actually works.
So let's recap. We've journeyed through the world of System Verilog today. We saw its evolution, its core identity as IE 1800, its comprehensive design features,
and its truly indispensable role in modern hardware verification, tackling that complexity challenge head-on.
Right. This language, really born from necessity, addresses the industry's critical need for productivity, for predictability, helping to reduce those costly chip failures and get products to market faster.
And its unified nature, covering both synthesizable design and powerful non-synthesizable OOP verification constructs, allows different engineering roles to work together effectively under one standard.
It's really incredible when you stop and think about this invisible language that underpins almost every piece of advanced tech you interact with daily. It leaves you wondering, though, As chips get even more complex, maybe designed with help from AI, what new challenges might System Verilog or whatever comes next need to tackle? How do we keep ensuring the reliability of our increasingly digital future?
That's the big question, isn't it? Constant evolution.
Definitely something to think about. We really encourage you, our listeners, to continue your own deep dives. Explore what stood out to you from today's discussion. Thanks for joining us.